Imagine a mathematical model where the initial conditions for a weather pattern were kept at three decimal places. A computer is made to solve and simulate a future event with those initial conditions. Then, on another day, these initial numbers are rounded to two decimal places and the calculations and simulations are done again. Do you think the end results would be similar or would digress substantially? Yes, so a butterfly flaps its wings. The movement moves some particles which were initially at rest to move. Then these particles enters into the nostrils of an engineer. The engineer sneezes and then forces out strong particles that is carried away by a small air current. These particles set off some particles in the lab close by, enters a test tube with a highly explosive material within, sets this material off, then boom, this explosion catches some other inflammable stuff and the whole lab is on fire. I know. There is an over exaggeration here, but that's the whole point about chaos theory. Chaos theory is an interdisciplinary area of scientific study and branch of mathematics. It focuses on underlying patterns and deterministic laws of dynamical systems that are highly sensitive to initial conditions. Chaos theory states that within the apparent randomness of chaotic complex systems, there are underlying patterns, interconnection, constant feedback loops, self-similarity, fractals, and self-organization. There is this set known as the Cantor set, and it is a simple set of infinite points that looks a lot in the inside but small on the outside. So to know about this set, just imagine a line. Take 1/3 of the line out from the middle. From the two sets remaining, take the third from the middle part and repeat this process forever. You started with one line, but you end up with an infinite number of points, all derivatives of this one line, and we term this Cantor set. Unpredictability is at the heart of chaos theory. Take a double pendulum and try to predict the movement of the second arm. It is almost impossible. The pattern of the second arm of a double pendulum is what we term chaos. But eventually, in the presence of friction, this double pendulum will eventually come to rest at a point. And this point we know, and that is the pattern we term a fractal in mathematics. A fractal is a curve or geometrical figure, each part of which has the same statistical character as the whole. They are useful in modeling structures in which similar patterns recur at progressively small scales, and in describing partly random or chaotic phenomena such as crystal growth and galaxy formation. So Lorenz, a meteorologist, reduced his parameters to three equations, and this is how those three equations behave. Yes, Lorenz was the one who performed those experiments with the computations using all those parameters, but then when the initial conditions were changed, that's varying, taking some aspect of his derivations from the middle part and using them as initial conditions, you are supposed to see that there is this concurrence with the first result, but then the results digressed substantially. Say you have a lot of items and you are taking the height of each of them at the x-axis, the width on the y-axis, and the color part perhaps on the z-axis. Then you introduce a fourth parameter, let's say time. When you record your values, you have this graph where all points seem to diverge, but they never meet. For one parameter, just like in the double pendulum, the final condition cannot be predicted with its initial conditions. But since the initial conditions of each item vary significantly, there is a complete change in their pathways. Nevertheless, they remain in this space mathematicians call the state space, where they seem to be confined, and therefore, for a set of parameters, their endpoints could be predicted somehow, and it's easier for a set than for individual parameters. Fractals often appear in living organisms where migrating cells can form fractals by clustering and branching. Nerve cells function through processes at the cell surface with phenomena that are enhanced by largely increasing the surface to volume ratio. As a consequence, nerve cells often are found to form into fractal patterns. These processes are crucial in cell physiology and different pathologies. Modeled fractals may be sounds, digital images, electrochemical patterns, circadian rhythms, etc. Fractal patterns have been reconstructed in physical three-dimensional space and virtually often called in silico modeling. What makes fractals possible is known as the Lorentz attractor, and it seems to be the reason behind the pattern being formed where all parameters converge somewhat. So, if we really want to know whether or not a swing of a butterfly's wing could cause catastrophe such as Chernobyl, then we will have to consider entropy all over again.